Hello everyone, let's discuss the operation of transformer under no load condition. So this is the circuit diagram for practical transformer. So we all know that in case of ideal transformer there are no iron loss and copper losses. So simply the losses are zero in case of ideal transformer, but coming to the practical transformer we have iron losses and copper losses. So in practical transformers there are two types of iron losses. Those are nothing but eddy current loss and hysteresis losses. So these iron losses are due to alternating nature of flux. So these iron losses are also supplied by the source. So we all know that in case of ideal transformer, the only component of current which is responsible to provide flux is nothing but magnetizing component of current, which is nothing but IM or IMU, which is responsible to provide flux in the transformer. This is for ideal. But coming to practical transformer, this current I0 is responsible to provide or to generate flux and to drive losses. So in case of ideal, only one component of current is there, that is magnetizing component of current. But coming to practical transformer, we have I0, that is nothing but no load current. This is I0 is nothing but no load current, which is nothing but combination of wattful component of current and magnetizing component of current. We will discuss in detail. So here this is the practical transformer representation. I2 is equals to 0. Why I2 is equals to 0? When the transformer is operating under no load, the secondary is open circuited, which means there is no load on the secondary, therefore the current in the secondary is 0, right? Because there is no load, that's why I2 should be equals to 0. So in order to drive the losses, iron loss component is nothing but what? Let us take IW. This component of current is responsible for supplying the iron losses. Those are nothing but hysteresis and eddy current losses. So and very small amount of copper losses in the primary winding under no load condition. Under no load, iron loss component is more, small amount of copper loss. Okay, so this current is responsible to provide iron loss component. This current is responsible to provide iron losses. So in order to drive these losses, some extra amount is needed. That current is nothing but IW. That's why in addition with that IMU, this IW is also adding. So this whole resultant is nothing but I0. This whole resultant is nothing but I0. But what is the combination of these two? The vector addition of this current, these two current is nothing but I0. That is I0 should be equals to IW plus IMU or IM. Okay, these two are the vector addition of no load current. I will discuss in detail between these two. So when the transformer secondary is open circuited, there is no current through that, obviously named as transformer under no load condition. So we all know that we have magnetizing component of current IM or IMU. Okay, like that active component of current IW. So under no load condition, you can write that point. Under no load condition, transformer draws two currents, IMU or IM, and IW. So these two are vector sum I naught should be equals to IW plus I mu, or you can write IW plus, in some textbooks they represented as IM, in some textbooks they represented as I mu. There is no problem at all, just you can follow whether it is IM or I mu. Okay, so the no load current consisting of two components, that the first one is what, reactive or magnetizing component of current. This reactive component of current is responsible to create the flux, right, also known as wattless component. Reactive component is nothing but what, wattless component. So it is in quadrature with the applied voltage. We will discuss in detail how it is quadrature with the applied voltage. Like that, it produces the flux in the core and does not carry any power. And coming to active power, IW, it is also known as working component of current. It is in phase with the applied voltage. We will discuss. It supplies the iron losses and small amount of primary copper losses. This current is responsible to drive the losses. In ideal transformer, we have only magnetizing component of current. This current is there in case of ideal. But coming to practical transformer, these two currents are there. That is the simple logic. Okay. So these are the very important points regarding to draw the phasor diagram. The function of the magnetizing component is to produce the magnetic flux, and this will in phase with the flux, right? We all know that. The induced EMF in the primary and the secondary winding lags the flux by 90 degrees. We have derived this relation between EMF and flux. The primary copper loss is neglected. Why it is neglected? Because less amount of copper losses are there, that's why they can be neglected. And secondary current losses are zero. Because why they are zero? Because I2 is equal to 0. Therefore the current lags behind the voltage vector by an angle phi naught. We all know that in case of ideal transformer, this current I mu lags V1 by 90 degrees, right? I mu lags V1 by 90 degrees in case of ideal transformer, but in case of practical transformer we are dealing with I naught. This I naught lags V1 by 90 degrees, sorry, V1 by some angle phi naught. So this is the phase angle between no load component of current and supply voltage, and this phi naught is nothing but phase angle. So obviously this is no load current, this is no load phase angle, obviously we have no load power factor. So the applied voltage V1 is drawn equal and opposite to the induced EMF. We all know that E1 should be equals to minus V1 or V1 equals to minus E1. We all know that. So active component IW is drawn in phase with the applied voltage. Like that, the phasor sum of magnetizing current I mu or IM and the working component of current gives the no load current I naught. So now I would like to explain in detail, just go through these points once. So this is the phasor diagram of the practical transformer under no load condition. Before the discussion of this phasor diagram, I would like to explain phasor diagram of ideal transformer. We all know that the flux is taken as reference, right? And this is what I mu, right? Only one component of current is there, that is I mu, and this I mu lags supply voltage by 90 degrees, right? This is 90 degrees. Okay, what about EMF? This is what, E1, this is E2, right? E1 should be equals to minus E1. And what is the phase displacement between these two? 90 degrees. Clear? This is the phasor diagram of ideal transformer. So what is the phase angle between voltage and current? Phase angle between voltage and current is 90 degrees. That is no load power factor which is equals to 0. No load power factor in case of ideal transformer is 0 because we have only magnetizing component of current only, but in case of practical transformer we don't have any magnetizing component. In addition with that magnetizing component of current, we have wattful component of current, that is I naught should be equals to vector addition of wattful component of current and magnetizing component of current, which is equals to resultant between these two, that is IW square plus IM square. That's why this I naught is the resultant between this IW and magnetizing component of current. So this I naught is nothing but what? Resultant between these two currents. Resultant between these two currents. Okay, sir, how can you draw this IW which is in phase with V1, IM which is in phase with phi? We all know that IM magnetizing component of current is always in phase with phi. Why always in phase with phi? The angle between this IM and phi is always 0 degrees. That's why this is in phase with current. But how it is in phase with V1? We all know this IW and IM are perpendicular to each other. This is IM is quadrature with V1, that is 90 degrees. And in order to give the clear cut explanation, I would like to take a simple inductive circuit. Let us take inductive circuit. We all know that for pure inductive circuit, current lags supply voltage by how many degrees? 90 degrees, right? So this is V1, this is I mu. For pure inductive, that's why this can be represented with what? Inductor. This component of current, I mu component of current, can be represented with what? The current through this coil is nothing but I mu. Clear? That's why there is a 90 degrees phase displacement between V1 and I mu. That's why in between these two 90 degrees phase displacement I mu and V1. Clear? And how can you represent the IW with in phase with V1? So we all know that IW is nothing but active component. We all know that the current through the resistor is always in phase with supply voltage, right? That's why this is the supply voltage. So this is IW. That's why it should be represented with what? A resistive part, a resistive element. This is what? IW. So the magnetizing component of current is represented with inductor, the active component of current is represented with the resistor. That's why IW is in phase with V1 and I mu or IM is quadrature with V1, because IW and magnetizing component of current IM and IW are perpendicular with each other. That's why IW is in phase with V1, IM is quadrature with V1 and which is in phase with flux, and the resultant between these two is nothing but what? No load current. And this is the phase angle between voltage and current, and this is the phase angle between voltage and current. This is the phasor diagram of practical transformer under no load condition. This is the phasor diagram of ideal transformer under no load condition, and this is the clear cut explanation for that. And these are the names for that. The working component of current is nothing but what? IW. So we all know that I naught should be equals to what? Square root of plus IM square, right? So from this IW is nothing but what? Cos phi naught. Why it is cos phi naught? This is active component of current. That's why this should be represented with cos. This should be represented with sine, because these two are quadrature with each other. That's why we have represented with cos theta, and this Im should be represented with I naught sine phi naught. From this, what is the power factor? No load power factor. No load power factor is what? IW, what? Full component of current by no load current. So no load power input, which is equals to V1 I naught cos phi naught. We all know that we have neglected the copper loss and we have only iron loss. Therefore this is nothing but iron loss approximately equal to iron loss under no load. Why copper loss are neglected? They are, since copper losses are neglected. So this is the equivalent circuit of transformer under no load condition. Why these two are connected in parallel? Because secondary is 0, open circuited. That's why there is no path through this winding. That's why the amount of current can be diverted. That's why this is I naught. I naught should be like this, and it can be split into what? 2, IW and I mu. We all know that I naught is equals to what? Perpendicular addition or vector addition of IW and IM. So IW and IM. That's why these two are connected in parallel. Why? Wattful component of current is represented with pure resistor, and magnetizing component of current is represented with inductor. Already I have given the explanation. This is the explanation for that. Okay, I mu lags V1 by 90 degrees. That is the case of pure inductor. That's why I mu is represented with pure inductor. But in case of wattful component of current, which is in phase with supply voltage, that's why it should be represented with pure resistive circuit. That's why IW through pure resistive element, I mu through reactive element, and the summation of these two gives rise to what? I naught only. KCL satisfied. That's why these two are connected in parallel. Why not in series? Because if these two are connected in series, there is no path for the flow of current, because secondary is open circuited. That's why in order to complete the loop, these two are connected in parallel. That is the important reason for that. Now I would like to give some important conclusions, observations. These observations are very most important. We all know that this is supply voltage, which is equals to minus E1. This is flux, and this is what? I mu. This is IW, right? This is in phase with V1. This is E1. This is E2. What is the resultant between these two? Up to this is what? Phasor diagram under no load condition of ideal transformer. But what is the resultant between these two? This is not I naught. So what is the phase angle between current and voltage? That is phi naught. So where phi naught is what? No load phase angle. No load phase angle. And cos phi naught is what? No load power factor. What is the value of power factor? Ideally, no load phase angle is what? Ideally, the no load phase angle is what? 90 degrees, right? See, ideally the no load phase angle is what? 90 degrees. Therefore, no load power factor is what? 0. This is for ideal transformer. But coming to practical transformer, practically phi naught should be equals to what? Approximately it is 70 to 75 degrees. This is what, which is equals to 70 to 75 degrees. Lagging. Why it is lagging? With respect to current only we have to tell. Why lagging? I mu lags, sorry, I naught lags V1 by, that is, you can write that point. From this, no load power factor is what? Cos of 70 to 7.5, we can get 0.22, 0.25 lagging. Why it is lagging? I naught lags V1 by phi naught. That's why it is lagging. Always it is operates with lagging power factor. This is the practical value of no load phase angle and no load power factor. This is the ideal value of no load phase angle and no load power factor. These two are very most important. Okay. And one more important, yeah, from this, these two are connected in series, parallel, right? So one more observation, that is, you can write that I naught should be vector addition of I naught and I mu. That is, I naught should be equals to what? Square root of plus I mu square. I mu is equals to I m. Whatever it may be, in some textbook they represented as I mu, or in some textbook they represented as I m. Okay. So from this we can write R naught, which is equals to, from this, to get this R naught, the voltage across this branch is nothing but what? V1 only. So V1 by IW is nothing but R naught. Like that, X naught is what? V1 by I mu. I naught, R naught equals to nothing but V1 by IW. Like that, and X naught should be equals to what? Supply voltage by I mu. And which one is more? We all know that I mu is far more than IW. Therefore, if I mu is more, R naught is far more than X naught, right? If I mu is more, R naught is far than X naught. Then what are the values of I mu and I m? I mu is 4% to 5% of full load current. Like that, IW is what? Just 1% to 2% of IFL. That is, I mu is 3 to 4 times of IW. So practically I naught should be equals to 5% of full load current. These are very, very important observation. I mu is far more than IW. That is, I mu is 3 to 4 times of IW greater. But practically, what is the no load current? 5% of full load current. That is where IFL is what? Load current. That is, we can say, that is, if IFL full load current 100 amps. Example, if full load current is 100 amps, therefore I mu or Im is what? Which is equals to 4 to 5%, that is 4 amps to 5 amps. Like that, IW, which is equals to what? Which is 1 amp to 2 amps. Like that, I naught should be equals to what? 5 amps. Combination of these two is nothing but I naught, which is equals to IW square plus I mu square. This is the explanation of this transformer under no load condition. Simple. The secondary is open circuited, obviously there is no secondary current. So in case of ideal transformer, only one component of current is there, that is I mu, which is responsible to create the flux. But in case of practical transformer, in order to drive the losses, some amount of additional current is required. That current is nothing but what? IW. So in this case of practical transformer, the summation of these two currents in summation of these two currents in vector form, obviously we are going to get I naught. So that current is there in case of practical transformer under no load condition. So we have two currents. These are the corresponding phenomenon of that corresponding IM and IW, and these are the main functions of these two currents. And this is the phasor diagram of transformer under no load condition. This phi naught is nothing but no load phase angle, and cos phi naught is no load power factor. This is the phasor diagram of transformer and ideal transformer. Practically phi naught is 70 to 75 degrees, but ideally phi naught is nothing but 90 degrees. That's why no load power factor for ideal transformer is 0. But coming to practical transformer, no load power factor is what? 70 to 75 degrees, that is 0.2 to 0.25. And how we can represent this wattful component of current through this resistor and magnetizing component of current through this reactive component. For that we have a reason, always magnetizing component of current lags V1 by 90 degrees. That's why we have to represent it with what? Reactive component, always wattful component of current in phase with V1, which is possible with respect to only pure resistor. That's why IW is represented through that resistive component of element. That's why this is the equivalent circuit. Why we have connected these two branches in parallel? Because secondary is open circuited. In order to complete the cycle, in order to provide the path for I naught, these two currents should be provided in parallel manner. These are the very important observations. And what are the observation? Ideally 90 degrees and no load power factor is what? 0 degrees. But practically no load phase angle is 70 to 75 degrees, and the power factor is what? 0.2 to 0.25. And these are the important observations regarding I mu, IW and I naught. Thank you.